Hey guys, my name is Cesar Hernandez, and I'll be talking about a brief summary on large language models and transformers and their role in artificial intelligence. First, we're going to talk about the introduction, large language models, transformers, and then a conclusion. To start off, large language models. What is a large language model? What does it do? So, we will explore how large language models have revolutionized the way we interact with AIs or artificial intelligence, particularly in the realm of text generation and chatbots. We will look how the models work, the training processes, and the underlying technologies that enables them to produce the content. To start off, we're going to talk about the basics of large language models. So large language models are inspired by the way humans use language to communicate and share knowledge. So the way I like to imagine it is, imagine you come across a movie script where there are actors which interact with AI assistants. However, the script includes character questions, but the AI responses are missing. So, in this situation, if you had a powerful machine capable of predicting the next word in a sentence, you could complete the dialogue by feeding the existence text into the machine and getting a response. That's essentially how a large language model works. However, that's not the underlying technology behind it. So, predicting the next word. At its core, a large language model is a sophisticated mathematical function that predicts the next word in the sentence based on the preceding text, which means, for example, if you put there was a boy, from that sentence, the large language model should give you some prediction of the next word. Either there was a small boy that was a king, for example, or any other text that may correlate to that previous uh, preceding text. So to train a large language models, there are three states: the scaling of the training data, the parameters and weights, and the computational challenges that come from it. So the scale of the training data, so to train a model like ChatGPT-3 takes an enormous amount of data, which is required, right? Since it is a large language model. So in this case, for humans to read a volume of text using ChatGPT-3, it would take over 2,600 years of continuous reading to read the amount, and larger models have more data that have been trained on, which means it might take even longer in human years to compute all of that. So next we have parameters and weights. We've talked about parameters and weights before, which are like the tuning mechanisms of the large language model. But in this case, it is determined by numerous parameters, often referred to weights. These parameters start at random values and have nonsensical outputs initially, which means the data is kind of like random. So if you give it a picture of a dog with a label of a cat, it'll be like, all right, this is the cat initially. However, with more training data, the more it's trained, and through more of its procedures such as backpropagation, ultimately the large language model learns to recognize patterns and labels. I would now like to talk about some of its computational challenges. We all know that large language models require a lot of computational resources. For example, if you could perform 1 billion operations per second, it would take over 100 million years to complete the training of the largest language model. This immense scale is only made possible by specialized computer chips, known as GPUs, which are optimized for parallel processing. I will now like to talk about pre-training and reinforcement. Pre-training involves the model learning to autocomplete random passages of text. For example, if you give it the quick brown dog jumped over, it should recognize the next word fence in that lullaby, you could say. So the goal is to effectively train the AI assistant to recognize some sort of passages from a random text. And then for reinforcement, pretty much a human worker evaluates the model's prediction, flagging unhelpful or problematic responses, and their feedback is adjusted back in the model's parameters, their weights, And then it produces a preferred output in the future. For example, in the example of the quick brown dog jumped over, it should be fence, the next word of its prediction, and so on. Next, I'd like to talk about the transformers architecture, which includes encoding language, the role of attention, and feed-forward neural networks. To start off, let me give you a background on the transformers architecture. So before 2017, most large language models process text sequentially, one word at a time. However, Google created a new model, which was later referred to as the transformer, which significantly improved that advances, which allow transformers to analyze text in parallel, allowing for more efficient processing. So encoding a language in a transformer, each word is associated with a list of numbers that encode its meaning. This encoding is crucial because the training process relies on continuous values. The unique aspect of transformers is to use operation called attention, which I'll talk about next, which pretty much means it interacts and refine their meanings based on the context. So the role of attention is to enable the model to adjust the encoding of words based on the surrounding context. For example, the word bank might be interpreted differently depending on whether it refers to a financial institution or a riverbank. This contextual understanding is vital for generating accurate predictions. And lastly, I like to talk about the feed-forward neural network. In a transformer, it also incorporates a feed-forward neural network, which enhances the model's capacity to learn and store patterns about the language. Through multiple iterations of attention and feed-forward operations, the model enriches its understanding of language, ultimately leading to more accurate predictions. In conclusion, the predictions generated by a large language model are often remarkably fluent and contextually appropriate. However, specific reasons behind the predictions can be challenging to decipher due to complexity of training processes and emergent behaviors of the model. So this is a good time to talk about transformers. So GPT, what is a transformer? So we will see how transformers specifically in large language models like GPT work. It explains the architecture, data flow, key concepts such as tokens, attention mechanisms, and training processes. Transformers have revolutionized fields of artificial intelligence, particularly in large language processing. So what is GPT? The initial stand for Generative Pre-trained Transformer. The term generative indicates that these models generate new text. Pre-trained refers to its extensive learning process, and transformer is crucial to denote specific types of neural network. So we have talked about transformer architecture in minor details, but now I'd like to discuss it in further details. So we can see other layers of the transformer architecture, such as the data flow in the transformer. So essentially is that it takes the data through the model step by step, and then transformer uses it for various tasks, such as translating text, generating images. However, we're going to focus on those of the ChatGPT and how it's trained to predict the next piece of text based on input. Also, think about tokens and vectors. When a transformer processes input, it first breaks the input into smaller pieces called tokens, and these tokens can be whole words, part of words, or common character combinations. Each token is associated with a vector, a list of number that encodes its meaning. Words similar, words with similar meanings are represented by a vector that are close to each other in a higher dimensional space. So, for example, the word boy, girl are going to be far apart from each other because they have no correlation. However, father and son have a closer correlation due to them either being referred to as male, both male types. And next, I'd like to talk about the attention mechanism. The vectors then pass through an attention block, which allow for them to communicate based on context. For example, the word model can differ based on the context in the sentence. The attention block determines which words are relevant to each other and how their meaning should be adjusted. And lastly, I'd like to talk about the multi-layer perceptron. After the tension block, the vectors go through a multi-layer perceptron, the MLP, or feed-forward layer, where they are processed in parallel. This step involves a series of operations to each vector, akin to asking a set of questions and updating vectors based on the answers. The key components of a transformer are its embedding matrix, the contextual understanding, and the context size. I'd like to discuss the embedding matrix first. So it is the first step in processing text, which involves converting tokens into vectors using an embedding matrix. The matrix assigns a unique vector to each token in the model's vocabulary, and then the vector are initialized randomly but refined during the training to capture semantic meanings effectively. And then as for contextual understanding, as the data flows through transformer, each vector can absorb context, allowing it to represent more nuanced meanings. For example, the vector for the word king may evolve to reflect specific context, such as being a Scottish king described in Shakespearean language. As for its context size, transformers have a fixed context size, which limits how much text they can consider before making a prediction. An example in GPT-3, the context size are 2048 tokens, which leads to challenges. As for the output generation, at the end of processing, the model generates a probability distribution over the next possible tokens that involves using an unembedding matrix to map the final vectors to the vocabulary size, followed by applying softmax functions to normalize the output. And I'll talk about softmax in a little bit. And then, so now we're going to discuss the softmax function, which pretty much transforms the raw input into probabilities that sum up to one. So at the end of all the predictions, the best prediction is going to be from either 0 to 1, 0 being the poorest, 1 being the highest. And in this case, it allows the model to make informed predictions about the next word, and it takes into account the temperature parameter, which can also be adjusted to influence the randomness of predictions, which affect the creativity of the text. In conclusion, understanding these mechanics of transformers provide an insight into how large language models like GPT operate. By breaking down the architecture, the data flow, and key components, we can appreciate the complexity and the capabilities of these models in generating coherent and contextually relevant text. Thank you for tuning in with me, and I'll see you on the next one.